All right, so we're going to take a look at review for the final. So first up, we're going to look at the things that are not covered in the other review videos. So here are some of the things that we did in Unit 4 that are not covered in the review video, and I'll show you again where to get those review videos. So first up, we just want to kind of look at some of the mini labs that we did. The first one was the Impulse mini lab. And if you remember that one, that was when we were designing our shoes and we were learning how cushioning affects the force. And we were dropping water bottles onto a stack of foam. And then we were registering how much force of impact that was. We also had a friction mini lab where we would have a shoe and you guys brought your own shoes in. You guys would pull it along the table with a spring scale and you would see how much force was required to pull it, basically telling us how much friction there was for the shoe. So again, some of the mini labs, we looked at the mass just to find out what the mass of the shoe was. We looked at stability, basically how stable the shoe was, how much you could tilt it before it actually falls over. And traction. And traction is looking at, again, sort of that force of friction. So in these cases, we wanted more mass or less mass. In this case, the lighter the shoe, the better in almost all situations. For stability, more stability was okay, right? More is better. If it's more stable than what you're asking for, that's great. And then for traction, again, more traction is usually better unless they specifically ask for less, like maybe the dancer might. But those were kind of the three mini labs that we were taking a look at. And there's a little video that you could play, but we're going to move past that. All right, so the next thing is, again, kind of going a little bit deeper into these. So the first one we want to go a little bit deeper into is looking at the impact. So again, as you step, right, there's an impact on your foot, on the shoe, and things like that. So we want to know how much of an impact that is. And this is where we were dropping the water bottle onto the foam that was sitting on a force sensor. Now we developed a word called impulse that helped us understand this process and what was kind of going on. And the impulse just measures the force applied over an amount of time that causes a change in momentum. And so a lot of times we kind of looked at it the other way around, where we were thinking about it in terms of that momentum change, that the water bottle was falling, it had to stop at some point. And so it has to go from moving to not moving. And there's a momentum change there. And that causes some sort of force, right? There's some sort of force that had to stop the water bottle. Now, what we learned was that if we increase the amount of time of impact, more layers of foam, right, helps cushion the landing, decrease the overall force on the water bottle. So it didn't require as much force if you were able to stretch out the amount of impact time. And that's, again, what the graph is showing here, that on the bottom here is time of impact. I don't know why it didn't show up, but as we increase the time, that force is decreasing. Again, here's sort of a way to look at it again. We've got our equation that we're taking a look at. Our mass times our change in velocity on the top. Time on the bottom. Those triangles just means change in velocity, change in time. And so for us, if we want to decrease that force, well, that means that we need to increase this number on the bottom. We need to increase the time in order to decrease the force. And again, we see that here in the table as well. As time increases, that force decreases. We can say it in words as well. When the time of impact gets twice as big, the impact force gets twice as small. And again, the picture's not a great one here, but again, it shows that inversely proportional relationship that we would expect from that statement. The other one that we were looking at was looking at friction. Now, we realized that friction had to do with definitely the structure of the bottom of the shoe, but it also had to do with how much weight there was in the shoe. We call that the normal force, how much force is pushing down on the shoe. And we realized that if we increase that downward force on the shoe, it really caused the shoe and the surface it was sliding on to get stuck together a little bit more and caused much more friction. So we realized that increasing the normal force increased the force of friction. And again, here we've got a little picture of what we did in the lab where we pulled on the spring scale, causing the shoe to slide. As we put more and more weight in the shoe, it made it harder to pull. Equation, force of friction equals friction coefficient, which is just kind of dependent on the surfaces, right? Some surfaces are more grippy than other surfaces, times the normal force. And so again, we can see on the graph that as the normal force, the weight increased, the force of friction was also increasing. We can see that in the table, that as the normal increases, force of friction also increases. We could say it in words, when the normal force gets twice as big, force of friction gets twice as big. They both get twice as big. And this is a proportional relationship, as we can see by the graph, as we can see by the words, as we can see by the table. The next thing that we did in this unit, and we did have a quiz on, was looking at the design priority. And so this is where we tried to figure out how, in the case of our client has certain needs, and we want to make sure that we are meeting the needs of that client. So in this case, we're going to look at a dancer, a little bit different than the dancer that you might have done when you were doing your project. But here's the information that we have about the dancer, right? We know that the dancer has a mass of 60 kilograms. That'll come up later. We know that the maximum amount of force that they want to feel is 600. If they feel less force than that, that's fine. The next one is stability. We want to make sure that this shoe is at least this stable, 35 degrees. So if the shoe can stay upright without tipping over at more than 35, that's great. That's even better. But we want to make sure that it's at least that stable. The next one is the mass of cushioning. So again, they don't want a very heavy shoe. So we want to make sure that their shoe is in fact light enough so that they can perform the things that they need to perform. It could be less than this, right? A lighter shoe is not a bad thing. And then, of course, what they want to do with it, sliding and dancing on floors and things like that. So again, we're just going to kind of look at each of these things and see how that fits in with our table. First thing we're looking at is the maximum mass. We said was 0.5. So in our shoe prototype table, we have a bunch of different prototypes, A through E. And they each have these different specifications. But if we're looking at the mass, the only three that work for us are prototypes A, B, and C. Those all are light enough that this person would be happy with their weight. They might not be happy with the cushioning. They might not be happy with stability. We'll deal with those later. But we're just looking at the mass right now, and they would be happy with all three of these in terms of how lightweight the shoe is. Next, we're going to look at stability needs. They want a shoe that is at least 35. Great. All of these shoes are able to withstand more than 35-degree tilt. So that's awesome. They would be happy with any of these shoes. The last one is the maximum force, the cushioning. and this one's a little bit more complicated. So they want 600 newtons of force. And so I've drawn in a line here that is at the 600 mark. Again, less force is good. More force is not okay, but less force is good. And because of their mass, right, the mass of the person itself is 60 kilograms. So we need to make sure that we're looking at this red line here. The red line is the 60 kilogram person. And so in this case, in order to have something less than 600, they would need 3 layers or 4 layers or 5 layers of cushioning. So if they had that many layers of cushioning, they would be perfectly happy because the impact force would be about 500 and something, right? Less than the 600 they wanted. If we gave them 4 or 5 layers, it would be an even smaller force, and they would be even happier about that. But we know that it has to be at least 3 layers of cushioning. So we can look at that, 3, 4, and 5. So in this case, the only 3 prototypes that they're happy with would be C, D, or E in terms of how much cushioning those shoes provide. Now we can put it all together. Again, we can see the stability. They were happy with any of them. Mass, they were only happy with A, B, or C. And cushioning, they were only happy with C, D, or E. So the only shoe prototype that works for our client is shoe prototype C because it works across the board. They're happy with it in every single way. They're happy with the amount of cushioning it provides, they're happy with the mass, and they're happy with how stable it is. So again, you guys would be expected to be able to do this. All right, those are the things that are not covered in the other reviews. So next thing we'll look at is look at the reviews. And so if we go to our Google Classroom, and I'm just going to pick 5th period, but obviously they're all the same. We scroll down. Again, I'll post them all together anyway, but we can go ahead and look at this test 5 review. I'm going to scroll down a little bit further and go back to the Unit 4 quiz review. So again, without replaying this video will show us how to do the math parts for that Unit 4, where we're looking at momentum, mass, and velocity. We're looking at force, mass, and acceleration, those types of things, so that we can kind of remember or remind ourselves how to do these types of fill in the table and then plot the graphs. Now, you do not need to remember the equations. We would always put the equation in there for you so that you guys could use it. You might need to rearrange it, as I did over here, where if I want velocity by itself, because that's what we're looking for, then you just need to rearrange it, right? And so you'd have momentum divided by mass to get velocity by itself. If you needed mass by itself, right? You just rearrange it so that it'd be momentum divided by velocity, equaling the mass. And then again, you can play the video, watch the video, and see how to do those calculations and figuring out what the plots are going to look like. And remember, you do not need a calculator. You do not need to simplify, as long as you can put the values in like I do here, where it's 10 over 1, 10 over 2, and so on and so forth. No need to simplify. All right, so that, again, is that Unit 4 review. Also, really good review for the tables and things like that. Helps out a lot. Back up here to Unit 5 review. Again, not going to play the video, but just a kind of quick reminder about what it goes through. It goes through all of the sort of definitions of terms for waves, what waves are, peaks, troughs, wavelengths, amplitude, frequency, all those different things, right? Showing you how to measure them as well. again, kind of looking through just all the definitions that were really important for the waves. Looking at how waves look when they are used in the simulation, things like that. Again, getting into sort of the math parts and the equations that we've dealt with. Again, you'll be given all the equations, so you don't need to worry about memorizing. You would just need to know how to plug things in if you're given a wavelength, if you're given a velocity, things like that. One key important, super important thing here is that unlike all the other equations, because the equations in physics are based on reality, some things are dependent on outside factors. For instance, what we're talking about here is the wave velocity. You cannot change the wave velocity by changing the wavelength or the frequency, right? Even though it looks like there's an equation, I can just change this number and it forces that number to change like you would in a normal math class. It doesn't work this way. In physics, the wave velocity is determined by the material that it's traveling through, not the wavelength, not the frequency. And so if you're given the wavelength in a problem, for instance, the wavelength is 3, and the wave velocity is 25, then you know that what's changing is the frequency, not the wave velocity. Can't change the wave velocity. So again, we've kind of got those tables, and you'd be able to fill those things out here. Again, it kind of goes through how to do that so that you guys can kind of see those things. Again, making sure that you guys can see that some things like amplitude are not in the equation, so making sure that you are understanding that it doesn't have any effect, right? Changing the frequency doesn't change the amplitude at all. It makes the peaks closer together, right? But it doesn't change how high those peaks are. So again, this is a good one to, again, watch through and review to kind of get the understanding of those waves. The last part is the sending a signal, the encoding and decoding stuff that we spent a lot of time looking at. If you were given something like a binary or digital code of zeros and ones, what would it look like in terms of an electronic, digital, or we call it voltage signal? What would it look like in terms of like an amplitude modulated or frequency modulated signal? And so being able to kind of try those things out and fill those things out. So zeros, again, would be the short amplitude. 1 would be the high amplitude. The zeros, again, short amplitudes. 1, the high amplitudes. Frequency modulated, again, either low frequency or high frequency. So low frequency would be the 0, high frequency would be the 1. Notice that the waves are just like squished closer together, right? That's what high frequency is. And remembering that we did tests with light and sound, and amplitude modulated light is bright light or dim light. Amplitude modulated sound is loud or quiet. Frequency modulated light is different colors. And a lot of you guys used like the red and the green and things like that. Frequency modulated sound is high pitch and low pitch. So different notes on like a keyboard or a piano or something like that. Again, watch those review videos. They've got a lot more detail than I went through in this short recap. But yeah, best of luck.